Welcome to Short Talks from the Hill, a research podcast of the University of Arkansas. My name is Matt McGowan. I'm a science writer here at the university. In 19 years at the University of Arkansas, there isn't much Min Zhou hasn't accomplished. Zhou is a professor of mechanical engineering in the College of Engineering and holds the 21st Century Chair of Materials, Manufacturing, and Integrated Systems. She is also an Arkansas Research Alliance Fellow. For the past 6 years, Zhou has served as director of the Multi-Institutional Center for Advanced Surface Engineering, made possible by a $24 million grant from the National Science Foundation through its experimental program to stimulate competitive research. This is otherwise known as EPSCoR. This and other EPSCoR grants have led to the creation of 2 companies based on Zhou's research. Zhou's work focuses on nano-surface engineering, that is, low-friction, lubricant coatings and surfaces for mechanical systems and other applications. Welcome, Min, and thank you for being here.
Thank you for having me. It's a pleasure to be here.
I look back and realize that I've been writing about your work for about 15 years. That's almost the entire time I've been here. It's probably too much to try to cover everything that you've accomplished over that span and longer, because you've been here 19 years. But I would like to go back to the beginning and have you define 2 big words as they relate to the essence, I guess, and longevity of your work. I'm going to try to pronounce them. One is hydrophobicity, and the other one is polytetrafluoroethylene. I think I got that right. What are these, and tell us how they are part of your research?
Yeah, I will start with the word hydrophobicity. Hydro comes from Greek hydro, which means water, and phobia comes Greek phobos, which means fear. So hydrophobicity means fear of water or lack of affinity to water. It is an often used word in the scientific community to define surface wettability. Surface hydrophobicity is often quantified by the water contact angle, which is the angle between the water-solid interface and water-air interface. If this angle is greater than 90 degrees, the surface is called hydrophobic. If this angle is greater than 150 degrees, the surface is called superhydrophobic. Superhydrophobic surfaces have many practical applications, such as self-cleaning, anti-icing, and anti-corrosion. For a surface to have superhydrophobic properties, both surface micro-nano topography and low surface energy chemistries are required. My lab has developed several techniques to fabricate various micro-nano topographies and low surface energy coatings, such as polytetrafluoroethylene or PTFE coatings for generating superhydrophobic surfaces.
If I could interrupt you there, that was a big relief. You're having trouble pronouncing it yourself after all these years, so I don't feel so bad.
Polytetrafluoroethylene.
PTFE. Tell us what that is.
PTFE is a fluorocarbon-based polymer. Consists of course, carbon and fluorine atoms. Carbons form slightly twisted chains. Each carbon atom is connected to fluorine atoms. They have very low surface energy, and the PTFE is better known for its brand name Teflon, which is widely used in cookware for its non-stick properties. However, there are many other desirable properties, such as low coefficient friction or slipperiness, low surface energy, and hydrophobicity, like we mentioned, high temperature resistance, and chemical resistance. So in addition, PTFE is also biocompatible. So it finds applications in biomedical implants as well as regular machineries like self-lubricating bearings, self-cleaning surfaces. So there are lots of applications of PTFE. However, one big challenge of applying PTFE as a coating is that it's non-stick, so therefore it's hard to stick to a substrate. Our lab has developed novel technologies to strongly adhere PTFE to a substrate, enable its durability and longevity.
In 2015, you and several colleagues received a $24 million in NSF EPSCoR funds to create the Center for Advanced Surface Engineering. Can you talk about this center? What do you do there? What do the researchers do at this center?
Yeah, so the center brought together 10 universities in the state of Arkansas, involving faculty, postdoctoral fellows, and students, working on developing new materials and surfaces with multifunctionalities and tunabilities. There are 4 main research thrusts for creating novel surfaces. The focus are on mechanical is one thrust, optical is another, cellulosic and medical applications that's the other thrust. So there are a total 4 research thrusts. The center research is highly interdisciplinary, involving various engineering disciplines like mechanical, chemical, biological, as well as physics, chemistry, biology, nanotechnology, material sciences. So there are different disciplines working together and come up with solutions to create surfaces that has potential applications. The center involved more than 60 faculty members, 90 graduate students, and 10 postdoc fellows, and over 100 students have participated in the center research. The researchers developed new technologies to make novel nanoparticles, 2-dimensional materials, engineered surface with special properties, such as the superhydrophobicity that we mentioned, as well as oleophilicity, which means oil absorbing capability. Well, this is very useful in like oil spill cleaning. As well as, of course, reduced friction, surface with reduced friction and longer durability, and antimicrobial properties, and many other properties that can impact manufacturing, healthcare, and environment. We also developed several new models that can model new materials, nanomaterials, cellulosic materials, coatings, and engineered surfaces. Overall, the center helped improve the research competitiveness of the state of Arkansas in the field of material science and engineering, and we continue to impact major industry sectors. Yeah.
The more recent work with a newer NSF grant, $500,000 to develop graphite lubricant coatings for conveyor belts, industrial conveyor systems. Tell us about that project.
Yeah, so in this project, we'll partner with industry leaders to develop low friction and durable graphite coating called solid lubricant for belt conveyor systems. Belt conveyors are widely used in many industries. You can imagine the airport, the distribution centers, FedEx, Amazon, UPS. And they are the fastest growing conveyor type. The global conveyor market is more than $5 billion per year, and flat conveyor market is like 26%, more than 26% of this market. However, they are not necessarily energy efficient. About 60% of the total energy in a flat conveyor system is used to overcome friction, a sliding friction between the belt and the sliding bed. So our goal is to be able to reduce that friction and improve the energy efficiency.
One of the exciting stories of your research here in your tenure at the University of Arkansas Tech Transfer, out of these EPSCoR funds, NSF EPSCoR funds, there have been at least 2 companies that have been created because of really based on your research. SurfTech is one, and Watt Glass, and some of my colleagues have written about these. Can you tell us about these companies and how they were created out of your work?
Yeah, so first I would like to mention that I have very talented and hardworking students who are dedicated to the commercialization of the technologies. So both SurfTech and Watt Glass were co-founded by my former PhD student to commercialize the technologies they worked on during their PhD dissertation in my lab. The SurfTech started with a commercialization effort by securing funding from the NSF, National Science Foundation, and Department of Energy to develop durable PTFE coatings for bearing applications based on my student Samuel Beckford's PhD research. They are now expanded the technology portfolio to anti-icing, anti-icephobic coatings that could have many applications. For example, anti-icing coatings could help prevent devastating disasters caused by the ice creation on the power generation system, like the one we have, the damage caused by the Texas ice storm last year. And of course, there are other applications as well. And they also developed lubricant sprays for industrial applications and ski wax for consumer applications. So an earlier company, Watt Glass, is also started with a commercialization effort based on Corey Thompson's PhD research. And he secured funding from the National Science Foundation and DOE to develop the anti-reflective, anti-fogging, and self-cleaning coating. That was research also supported by a previous EPSCoR grant when he was a graduate student. They are now broadening. Those are for solar panel applications to start with. Now they are broadening the applications to street lights to improve the energy efficiency of these products. My lab currently has several novel technologies that have commercialization potential. We hope to continue to apply these new technologies to benefit the state of Arkansas and the world at large.
Thank you so much for being with us today, and I look forward to talking to you some more about your research in the future.
Okay, thank you.
Music for Short Talks from the Hill was written and performed by local musician Ben Harris. For more information and additional podcasts, visit Arkansas Research. That's arkansasresearch.uark.edu, the home of science and research news at the University of Arkansas.